Welcome back to the Deep Dive. Today we are doing something a little dangerous. We are not just exploring a new idea.
No.
We are taking a sledgehammer to the very bedrock of your reality. And I promise you, I am not exaggerating.
Not at all.
We are looking at a stack of research, lectures, and books, all centered around the biologist Rupert Sheldrake and his hypothesis of morphic resonance. And to kick things off, I have a question for you that might sound like, well, complete nonsense at first, but just bear with me.
Okay, I'm ready.
What if the laws of physics aren't actually laws at all? What if they're just habits? Habits that the universe picked up along the way?
It's the kind of question that gets you kicked out of a university physics department, isn't it?
It really is. I mean, we are trained, conditioned, really, to believe that the laws of nature are these commandments.
Absolutely. Unchanging.
Gravity, the speed of light, the charge of an electron. These things were etched in stone at the moment of the Big Bang, and they haven't budged a millimeter since.
They're eternal. Fixed.
But Sheldrake looks at this and says who? What if they're just habits? What if the universe is actually learning as it goes along?
It's a massive pivot in perspective. I mean, you have to shift from seeing the universe as a machine.
Right, like a clock.
Like a clockwork mechanism that was wound up once and just runs. You have to start seeing the universe as an organism.
An organism.
Yeah, a machine has fixed software. An organism has memory. An organism develops habits. Sheldrake is suggesting that nature itself has a memory.
A memory of nature.
And what we call laws are just the habits that have been repeated so often they look permanent.
And before you, the listener, think we're about to spend an hour discussing, abstract philosophy, I want to be clear. This theory is trying to solve some very embarrassing, very expensive problems in hard science. We're going to talk about pharmaceutical companies losing hundreds of millions of dollars because their chemicals suddenly forgot how to work.
It's an amazing story.
We're going to talk about rats in Melbourne, somehow, knowing what rats in London learned yesterday.
And we're going to talk about why you might be better at Wordle in the evening than you are in the morning.
Which is my favorite part, definitely. But let's start with the foundation. Why are we so obsessed with the idea that the laws of nature are fixed?
Yeah.
Because until I read through this material, I assumed that was a proven fact. I didn't realize it was actually a cultural assumption.
It's a huge cultural assumption, and it's one with a lot of baggage. To understand why scientists get so angry at Sheldrake, you have to realize that he's attacking their theology.
Theology? I thought science was the opposite of theology.
Well, let's look at the history. The standard model of reality. The materialism we learn in school. It really dates back to the 17th century. But its roots, they go way deeper.
Where to?
Back to the ancient Greeks. Sheldrake points specifically to Pythagoras.
The triangle guy.
Right.
A squared plus b squared?
The triangle guy, yes. But Pythagoras wasn't just, a guy doing homework. He was a mystic. When he discovered that musical harmonies corresponded to simple mathematical ratios, whole numbers, he had a religious experience.
Wow.
He believed he had looked under the hood of the physical world and found the real world. To him, the messy world of dirt and trees and flesh was just a shadow.
So the real world was math.
The real world was a world of eternal, perfect mathematics.
So the idea is that somewhere out there, in a non-physical realm, there is a perfect version of a circle or a perfect equation for gravity, and our universe is just a clumsy copy of it.
Precisely. Plato took this and ran with it, the theory of forms. He believed that the physical world is always changing and decaying, but the world of forms of ideas is eternal and unchanging.
Okay, so that's the ancient world. How does that connect to modern science?
Well, fast forward to the 17th century, the scientific revolution. The founding fathers of modern science, Newton, Descartes, Kepler, they were all deeply religious men. They didn't want to get rid of God. They wanted to understand how God built the universe.
Oh, they adopted this Greek idea.
They adapted it. They decided that these Platonic forms, these eternal mathematical truths, were ideas in the mind of God. God was the ultimate mathematician. He wrote the code. And because God is eternal and unchanging, the laws he wrote must be eternal and unchanging.
So the laws of physics are basically secular theology.
Exactly. And this is where Sheldrake makes this biting analogy about the high priests.
The high priests.
Even today, modern materialist scientists who might be staunch atheists still treat mathematics with this religious reverence. They believe the math exists out there, independent of the universe.
It's like the code existed before the computer was even built.
Right. And if the ultimate reality is this invisible, eternal math, then who are the only people capable of contacting that reality, who can read the mind of God?
The people who speak the language.
The mathematicians.
They become the priesthood. They are the intermediaries. So when Sheldrake comes along and says, actually, maybe the laws aren't eternal, maybe they evolve, he isn't just proposing a new theory.
He's committing blasphemy. He is. He's telling the high priests that their God is just a habit.
That really puts the hostility he faces in perspective. It's not just a disagreement about data. It's a heresy trial.
It really is.
And this connects to that brilliant quote from Terence McKenna regarding the Big Bang. I laughed out loud when I read it because it's so accurate.
Modern science consists of one free miracle, and then we explain the rest.
It's so true. The Big Bang Theory basically says, okay, give us one moment where all the matter, all the energy, and all the laws of physics appear instantly out of nothingness.
Just give us that one.
Just give us that one impossibility. After that, we promise everything will be strictly cause and effect.
It's a massive ask, and it creates a huge problem called the fine-tuning problem.
Right.
If the laws appeared instantly, why are they so perfectly tuned for life? If the force of gravity was slightly stronger, stars would burn out in a week. If it were slightly weaker, matter would never clump.
So why did the Big Bang roll the dice and get a natural 20 on the first try? And the standard scientific answer to that is the anthropic principle, right?
Mm-hmm.
Well, we're here to observe it, so it must be right, which always feels like such a cop-out.
It is a tautology. It's just saying it is what it is because it is what it is. So to get around that, materialists have invented the multiverse.
The multiverse. This is the idea that there are, what, infinite other universes?
Yes. If you can't explain why this universe is perfect, you just assume there are quadrillions of other universes that are broken.
So some have no gravity, some have too much.
Right. And we just happen to be living in the one that works.
But there's zero evidence for that. We haven't seen these other universes.
Zero. And Sheldrake had a conversation with a physicist friend about this. He asked him, you admit there's no evidence for these infinite universes. Why do you insist on them?
And what did he say?
And his friend said, because it's the only way to avoid God.
Wow. So they are willing to invent an infinite number of invisible realities just to avoid admitting that the laws might have a purpose or an evolution.
It's the ultimate violation of Occam's razor. Occam's razor says the simplest explanation is usually the right one.
Don't multiply entities unnecessarily.
And materialism invents infinite universes to explain one. Sheldrake says, I have a simpler idea. Maybe the laws aren't fixed.
Maybe they evolve?
Maybe the universe evolved. Maybe the gravitational constant is just right because it grew up alongside the universe.
That's like saying, my genes fit me perfectly. The multiverse theory says, that's because you tried on a billion pairs of jeans and found the one that fit.
Right.
Sheldrake says, no, it's because the jeans are made of spandex and they stretch to fit me.
That is a fantastic analogy. Yes, the laws stretch. They adapt.
Okay, so let's get into the mechanics of this stretching. The theory is called Morphic Resonance. It sounds very sci-fi, almost magical. How does it actually work? What's the mechanism?
So the technical definition is similar vibratory systems influence subsequent similar systems across space and time.
Okay, hold on. Similar vibratory systems. That could mean anything.
It sounds vague, I know, but think about physics. Everything is vibration. An atom is a vibrating system of energy. A molecule is a vibrating structure.
A cell, an organ.
A cell, an organ, a giraffe, they are all patterns of activity. Sheldrake argues that when a system is forming, let's say a protein folding into a shape, it doesn't just rely on the laws of physics in that immediate vicinity.
So what does it do?
It tunes in.
Tunes into what?
To the past. It resonates with every other protein of that type that has ever existed. It draws upon a collective memory of how this protein is supposed to fold.
So it's not looking at a blueprint, it's looking at a history book.
Exactly. And the more similar the system is, the stronger the resonance. A giraffe embryo resonates with all past giraffes, but it resonates most strongly with its own parents and recent ancestors.
Because they're the most similar.
Because they are the most similar.
One thing I noticed in the reading is that Sheldrake is very particular about the words he uses. He hates the word information. He prefers form. Why that distinction?
This is crucial. We live in the information age, so we think of everything as data. We think DNA is code. We think the brain is processing information.
Right.
But Sheldrake points out that information implies a sender and a receiver. It implies a signal, like Morse code, or a radio wave carrying a voice.
Right. If I send you an email, I am packaging information and sending it to you.
But in nature, there is no sender. When a crystal forms, nobody is sending it a memo.
Right.
Sheldrake uses the word form, or information in the literal sense, to put form into something. It's about structure, pattern. It's not a code being deciphered, it's a shape being echoed.
So it's closer to like a tuning fork.
Yes, that's a great way to put it. If I strike a tuning fork in one corner of the room, and there's a silent tuning fork of the same frequency in the other corner, what happens?
The second one starts to vibrate.
The second one will start to vibrate. It resonates. No information was sent, no code, no language, just a resonance of form.
Okay, that makes sense conceptually. But now we have to face the skeptics. Because if I'm a hard-nosed scientist, I'm saying, show me the money.
Right. Where's the proof?
You can't just say the universe has habits. You have to prove it. And this is where Sheldrake pivots to chemistry. And honestly, this is the part that really shook me. Because rocks and chemicals aren't supposed to have memories.
That's why the chemistry evidence is so powerful. If we were just talking about psychology, you could argue it's culture or, social learning.
But chemicals don't go to school.
They do not.
So walk us through the crystals that learn phenomenon.
Okay, the premise is simple. If you create a brand new chemical in the lab, something synthetic that has never existed in the history of the universe, there's no habit for it yet.
No memory.
No memory. The atoms don't know how to arrange themselves into a solid crystal lattice.
They're confused.
They're lost.
Sure.
So the first time you try to crystallize a new compound, it's notoriously difficult. It might stay as a sludge or a liquid for weeks, months, even years.
I've heard chemists talk about this, stirring and praying.
That's literally what they call it. But then eventually it happens.
By chance.
Eventually, by chance or brute force, a crystal forms. The atoms lock into a pattern. A form is created. Now, according to standard science, that shouldn't affect anything outside that one beaker.
But according to Morphic Resonance,
a new habit has just been born. And suddenly, all over the world, it should become easier for that chemical to crystallize.
And we have a specific example of this, xylitol, the stuff in my gum.
The stuff in your gum. Xylitol was first discovered in 1891, but it was a liquid, a syrup. For 50 years, 5 decades, chemists listed xylitol as a liquid.
It just wouldn't crystallize.
It simply wouldn't crystallize. They tried cooling it, heating it, you name it, nothing worked.
And then?
1942. Suddenly, in a lab, it crystallized. It had a melting point of 61 degrees Celsius.
Okay, so they finally figured out the trick. Some special procedure.
But here's the thing. It wasn't a trick. They didn't invent a new machine or a new process. It just happened.
It just decided to crystallize.
And once it happened there, it started happening everywhere. Chemists who had been staring at liquid xylitol for years suddenly found their samples turning solid. The habit had spread.
That is weird. But the story gets weirder, right? Because the crystal changed again.
It did. About 20 years later, a new form appeared. A polymorph. This one had a melting point of 94 degrees Celsius.
So it was more stable.
Much more stable. A tighter lattice. And here's the Twilight Zone moment. Once the 94-degree form appeared, the 61-degree form vanished.
Vanished? What do you mean vanished?
You couldn't make it anymore. The universe forgot the old habit because the new habit was stronger. The atoms preferred the deeper groove of the 94-degree form.
So you can't make the old one anymore?
No. If you try to make the 1942 version of xylitol now, you basically can't. The laws of nature regarding xylitol effectively changed.
That sounds like magic. But you mentioned something even more dramatic. A corporate disaster. The ritonavir case.
Yes.
This isn't just a curiosity. This is a company almost going bankrupt.
Abbott Laboratories. This is the case that keeps pharmaceutical executives up at night. Ritonavir was a blockbuster AIDS drug in the 90s. It was saving lives, and it was making a fortune. It was manufactured as a specific crystal, let's call it Form 1.
And it worked?
It worked perfectly. It was soluble, meaning it dissolved in the stomach so the body could absorb it. But then, in 1998, after 2 years of mass production, the factory line started failing.
Failing how?
The drug wasn't passing the quality tests.
What?
The crystals had changed shape. A new polymorph Form 2 had appeared, and Form 2 was a disaster.
Oh, so?
It was much more stable, which sounds good, but it was too stable. It was like a rock. It wouldn't dissolve. If a patient took the pill, it would just pass right through them.
So the drug was completely useless?
Useless. Abbott went into crisis mode. They assumed it was contamination. They formed emergency task forces. They scrubbed the factory walls. They tore out the piping.
Oh, wow.
They replaced the ventilation. They brought in hazmat teams to eliminate any seed of this new crystal.
They were trying to exorcise the factory.
They were, but it didn't work. And worse, scientists in other labs around the world who had samples of the original formar in sealed jars went to check their shelves and found that their samples had turned into form too.
Inside sealed jars.
Inside sealed jars. The infection wasn't physical, it was resonant. The morphic field of ritonavir had shifted to a more stable state, and every molecule of ritonavir in the universe fell into line.
What was the fallout from that?
Abbott lost $250 million. They had to pull the drug and completely reformulate it as a liquid gel just to get it back on the market.
Now, I have to play devil's advocate here. Because surely the chemists at Abbott didn't say, oh, well, morphic resonance got us.
No, they did not.
They must have a scientific explanation for this.
They do. It's called disappearing polymorphs. But their explanation is, well, it's lacking. They blame it on unintentional seeding.
Dust. You mean like a piece of dust carried the new crystal shape?
Dust. The theory is that maybe a microscopic crystal of the new form traveled on a lab coat or blew in the wind from one lab to another.
From Chicago to Tokyo, on the wind.
That's the stretch. Sheldrake quotes a textbook on polymorphism by Joel Bernstein, essentially the Bible of this field, and even the textbook admits this is a weak explanation.
So even the experts don't really buy it.
They admit there's no consensus on how these seeds could survive travel, how they get into sterile rooms, or how they move globally so quickly. Seeding is just a placeholder word for, we don't know how this happened, but it can't be magic.
It's the swamp gas of chemistry.
Exactly. It was just a weather balloon.
Okay, so we have individual stories. Xylitol, ritonavir. But stories are anecdotes. Does Sheldrake have big data to back this up?
He does. He discusses a study by a chemist named Classer regarding melting points. Now, melting point is supposed to be a constant. Water freezes at 0, boils at 100. It doesn't change.
Right.
But if crystals are learning to be more stable, their melting points should be rising over time.
Why rise?
Because a higher melting point means the crystal is holding together tighter. It takes more heat energy to break the lattice apart.
Makes sense.
So Classer looked at the melting points of 149 synthetic chemicals measured throughout the 20th century.
Synthetic, so new chemicals.
Yeah.
The ones that are still learning.
Right. And he found a massive trend. The melting points of 141 of them went up.
141 out of 149.
Yes. Only 8 stayed the same or went down.
That's not a margin of error. That's a landslide.
It is. Now, the skeptics have a very good counter-argument here. Purity.
We just got better at chemistry over the century.
Correct. In 1900, our samples were dirty. Impurities usually lower a melting point, like how salt melts ice on the road.
So as we got better at purifying chemicals, the melting points naturally rose to their true value.
That's the argument.
That sounds incredibly logical. It almost debunks the whole thing.
It would if Sheldrake hadn't thought of a control group. He compared these synthetic chemicals to natural chemicals, things like salicin from willow bark. These chemicals have existed for millions of years.
So their habit is ancient, it's fully formed, there's nothing left to learn.
Exactly. The groove is deep. And guess what? The melting points of natural chemicals didn't change over the 20th century.
At all.
They were flat.
Even though we got better at purifying them, too.
Exactly. If the purity argument was the whole story, salicin's melting point should have gone up too, but it was flat. Meanwhile, aspirin, which is a synthetic derivative of salicin made by humans, saw its melting point rise by 9 degrees.
Whoa.
Cocaine is another one. Natural cocaine from the leaf. Stable. Processed cocaine hydrochloride that we make in a lab. Its melting point went up 14 degrees.
That is the nail in the coffin for me. The man-made stuff is learning. The nature-made stuff is finished learning.
It strongly suggests that what we call constants are just mature habits.
Okay, let's leave the lab and go to the barn. Because if dead matter can learn, living matter should be even better at it. And Sheldrake brings up the rats.
The famous rats, yes.
He starts with Pavlov. Now, we all know Pavlov for the drooling dogs, but he did a really weird experiment with mice.
He did. He tried to teach mice to run to a feeding spot when a bell rang. It seems simple, but for the first generation of mice, it was incredibly hard.
How hard?
It took them 300 trials to learn the association.
300? That's a stupid mouth.
Shuckles, or a hard task. But then Pavlov bred them. The second generation learned it in 100 trials, the third in 30. By the fourth generation, they were learning it in 10 trials.
Okay, skeptic hat on. Evolution. He was just breeding the smart ones. Simple selection.
Except he claimed he wasn't selecting for intelligence. He was breeding the whole line. But the real proof comes from the water maze experiments done later at Harvard, Edinburgh, and Melbourne.
So this is a global effort, separate continents.
Yes.
Yeah.
Rats at Harvard were trained to escape a water maze. Over generations, they got faster. That's expected. But then they tested rats in Edinburgh and Melbourne.
And these were unrelated rats.
Completely unrelated. Same breed, but no genetic connection to the Harvard rats.
So they shouldn't know the maze. They should be starting from scratch.
They shouldn't. But when they were put in the water, they started at the same proficiency level that the Harvard rats had effectively reached. They knew the maze. And crucially, the control group, rats whose parents had never seen a maze, also improved.
Wait, that's the key. If the control group is improving, it can't be genes.
Exactly. If it were genetic selection, only the offspring of the maze-running parents would be smarter. But if all rats of that breed are getting smarter at water mazes, the improvement isn't in the DNA.
It's in the field.
It's in the field. The species is learning.
That is mind-bending.
Yeah.
It means we are all, in a way, tapping into a global brain of our species.
Which brings us to the cherry blossom experiment. This one is genuinely terrifying. And it was published in Nature, so this is top-tier science.
This is the inherited fear study.
Yes. They took male mice and exposed them to the smell of acetophenone, which smells like cherries or almonds.
Okay.
Every time the mouse smelled it, they gave it a mild electric shock.
Standard conditioning. Smell cherries equals get zapped.
Right. The mice learned to be terrified of the smell. But then they took sperm from these mice and artificially inseminated females. The fathers never met the mothers, and they never met the babies.
So no chance for the dad to say, hey, kid, watch out for the cherries. No social learning.
None. But the babies and the grandbabies were born terrified of the smell of cherries.
I have heard this explained as epigenetics. That's the big buzzword right now.
It is. And it's the safe explanation. Epigenetics involves things like DNA methylation, little chemical markers that attach to the DNA and switch genes on or off.
So the idea is the shock caused a chemical switch to flip, and that got passed down.
That's the standard view. Look, the shock caused a methylation change, and that was passed down.
That sounds plausible. Why does Sheldrake reject it?
He doesn't reject that methylation happens. He rejects that it explains the memory. Think of it this way. Epigenetics is like a volume knob. It can turn a gene up, making the mouse more sensitive to smell generally, or turn it down. But a volume knob cannot write a song.
I like that. A volume knob can't write a song.
How can a simple chemical switch encode the specific complex smell of acetophenone and link it to the specific emotion of fear? That's information. That's a complex pattern. A switch is just on-off.
So epigenetics is the hardware adjustment.
But morphic resonance is the signal transmission. The mouse inherits the volume up from the genes, but it tunes into the fear of cherries song from the morphic field.
That distinction is really helpful because otherwise you're asking a chemical tag to do a lot of cognitive heavy lifting.
Exactly. And this problem of genes can't explain it all is actually a huge crisis in biology right now. It's called the missing heritability problem.
We spent billions on the Human Genome Project. We thought we'd find the gene for height and the gene for IQ.
And we failed miserably. Take height. It's very heritable. Tall parents have tall kids. But if you add up all the genes we found that affect height, they only explain about 60–65% of the variation.
So where's the other 35%?
That's the missing part. The genes simply aren't enough to build the body.
So Sheldrake says the genes are just the building materials, but the blueprint comes from the field.
Yes. And this explains the twin paradox.
Identical twins separated at birth.
They often lead startlingly similar lives. They give their kids the same names, they like the same obscure foods, they fall down the stairs at the same age.
And science usually just says, wow, genes are destiny.
But Sheldrake says, no, they are telepathic. Remember, resonance works on similarity. Who is the most similar person to you in the world? Your identical twins.
Right, your DNA is a perfect match.
Your DNA is a perfect match. Your brain structure is a perfect match. You are tuned to the exact same frequency.
So they are constantly uploading and downloading from each other, even if they're continents apart.
Exactly. They are resonant partners. It's not that the gene for naming your dog Spot was in their DNA. It's that one twin named the dog Spot, and the other twin picked up the resonance and thought, you know, Spot sounds like a good name for a dog.
That completely reframes the nature versus nurture debate. It adds a third player. Resonance.
It does. It's nature, nurture, and resonance.
Okay, let's bring this home to us humans. Because if rats are learning from other rats, are we learning from other humans? Are we downloading skills? You bring up the QWERTY keyboard.
The layout we all love to hate.
I actually didn't know the history of this. It was designed to be bad.
Mechanically, yes. On the old typewriters, if you typed T and H too quickly, the metal bars would crash into each other and jam the machine.
I see.
So the QWERTY layout was designed to separate common letter pairs. It was literally designed to slow you down.
So we are using a bottleneck design on touchscreens that have no metal bars to jam.
Correct. It's irrational. So back in the day, IBM tried to fix this. They spent a fortune designing ergonomic keyboards. They arranged keys alphabetically or based on frequency.
And they must have been faster.
Right. On paper, they were superior, but in practice, it was a disaster. Even when they tested these better keyboards on people who had never typed before, total novices, those people still learned QWERTY faster.
That makes no sense. A novice shouldn't have a bias.
Unless the bias is in the field. Sheldrake argues that because billions of people have typed on QWERTY for 150 years, the skill of finding the A and the P is deeply etched into the human collective memory.
So a kid today isn't starting from scratch.
They're not. They are drafting behind billions of typists. The habit of QWERTY is so strong it overrides the bad design.
We are inheriting the muscle memory of the 20th century.
In a way, yes. And this applies to puzzles, too. You mentioned Wordle.
I swear the crossword is easier in the evening. My wife and I always say this.
And you're likely right. There is data on this, the daily puzzle effect. As the day progresses and more people solve the puzzle, the solution path becomes a well-trodden road in the morphic field.
So it becomes easier for later solvers to find the answer.
It does. They've even shown with Wordle that people get luckier guessing the word on the first or second try more often as the day goes on globally.
So my lucky guess at 8 p.m. isn't luck. It's me surfing the wave of a million other people's success.
It puts a dent in our ego, but it connects us, and it explains the Flynn effect.
The Flynn effect. That's the thing where IQ scores have been rising for a century.
Yes. We are answering abstract logic puzzles 30% better than our grandparents did.
I always heard that was nutrition. We have better brains because we eat better food.
That's part of it. But the biggest gains are in abstract pattern recognition, the kind of stuff you see on IQ tests. Sheldrake suggests that because millions of people have taken these tests, the logic of the test has become a human habit.
The answers are in the cloud, so to speak.
The answers are in the cloud, and we have better Wi-Fi access to the solutions.
Answers in the cloud. That's the perfect transition to the most radical part of this theory. The brain.
The receiver.
If memories are in the field, if habits are in the field, then they aren't in my head.
This is where Sheldrake upsets the neuroscientists. We are taught that the brain is a hard drive. You have an experience, the brain encodes it into RNA or protein, stores it in a synapse, and retrieves it later.
But Sheldrake says,
no.
He says no. The brain is a TV set.
The TV analogy is so sticky. It's so good. It is. If you damage your TV screen, the picture gets fuzzy. If you smash the audio chip, the sound stops. But that doesn't mean the TV show is being created inside the TV.
The show is a broadcast. The TV just tunes into it.
Exactly.
So if I get a concussion and lose my memory, I haven't wiped the hard drive. I've just bent the antenna.
You've bent the antenna. The memory exists, but you can't access it. This explains why memories often come back after trauma heals. If they were physically destroyed, they'd be gone forever.
Is there actual evidence that the brain isn't a hard drive? Because we see brain scans, we see the lights. It looks like it's all happening in there.
We see activity, but correlation isn't location. And the search for the physical enneagram, the memory trace, has been a century of failure.
Tell me about Lashley and the rats. This sounds gruesome.
It was. Carl Lashley, back in the mid-20th century, tried to find where a rat stored the memory of a maze. He reasoned, if I cut out the memory part, the rat will forget.
Simple enough.
So he trained rats, then surgically removed chunks of their cortex. 10%, 20%, 50%.
And the rat forgot.
It didn't. It got clumsy. It limped. It went blind in one eye. But if it could physically drag itself through the maze, it still knew the way.
He couldn't find the spot.
He couldn't find the spot. He concluded memory was everywhere and nowhere at the same time.
That sounds impossible if memory is a physical file. You can't cut out half a hard drive and still have the file perfectly intact.
Exactly. And modern science has found something called representational drift, which is even more puzzling.
What's that?
Okay, imagine a card stunt at a football stadium. The crowd holds up cards to make a picture of a flag.
Okay, I can picture that.
You take a photo, You see exactly which people are holding up cards. That's the memoral. Now, come back a week later. The flag is there again. It looks identical. But when you zoom in, it's a completely different set of people holding the cards.
The pattern is the same, but the physical stuff, the people, has changed.
That is what happens in the brain. The specific neurons that fire when you learn a task are different from the neurons that fire when you remember it a week later. The physical representation drifts.
But if the memory was stored in the connections of those first neurons,
it should be gone when those neurons stop firing, but the memory persists.
That really challenges the materialist view. And then there's what you call the granny argument.
Simple biology. Your brain proteins turn over constantly. They are replaced every few weeks or months. Sheldrake mentions his 100-year-old grandmother. She remembered her childhood vividly.
Right.
But the brain she had at 100 was made of completely different atoms than the brain she had at age 10. Every molecule had been replaced.
So how can a 90-year-old memory survive on a hard drive that replaces its own disk every month?
It can't, not unless the memory is stored outside the hardware.
And this leads to terminal lucidity. This is the one that really gets me emotional.
It's a profound phenomenon. You have Alzheimer's patients who have been non-responsive for years. Their brains are physically atrophied, full of plaques and tangles.
The hard drive is melted?
The hard drive is melted. They don't know their kids. They can't speak. And then sometimes just hours before death, they wake up.
They wake up.
They sit up. They recognize everyone. They have a coherent conversation. They access their full memories.
How is that possible?
If the memory was in the destroyed tissue, it's impossible. You can't recover data from a melted disk. But if the brain is a receiver and the dying process somehow loosens the tuning or bypasses the damaged filter, then the mind can tune into the field one last time.
The signal was always there. The set was just broken.
The signal was always there.
That implies that consciousness isn't produced by the brain. It's transmitted through the brain.
Which opens the door to everything. Life after death, telepathy, spiritual experiences. It's all on the table.
Speaking of things that might be conscious, AI. We have to ask, does ChatGPT have morphic resonance?
Chuckles. Sheldrake was asked this, and his answer is probably not.
Why not? It learns incredibly fast.
But it's not a self-organizing system. Morphic resonance requires the system to organize itself, like a crystal growing or an embryo developing. A computer is a machine. We put the chips together, it's rigid.
So it's too mechanical to resonate.
Yes. However, he did mention quantum computers because they rely on probability and indeterminacy. They are fuzzy like nature. They might be able to tune into the field, but your standard server farm, no.
I loved the detail that Sheldrake is just annoyed by AI.
Yes. He's getting spammed. People are asking AI to combine Sheldrake's theory with string theory, and then they email him the results.
And he's not impressed.
He calls them hallucinations. He wants AI to do the boring work like crunching all that melting point data. But instead, it's trying to be a philosopher.
It wants to be a high priest, too.
Everyone wants the job.
So we've covered the history, the chemistry, the biology, the brain. I want to land on the so what for a listener. Because this changes how I see myself. If memory isn't in my brain, what happens when my brain dies?
Sheldrake hints that if the memory is in the field, it doesn't necessarily vanish. And he tells a story about a heart transplant that is truly chilling.
The surgeon story.
A transplant surgeon who had a cardiac arrest went into a coma and needed a transplant himself. While he was in the coma, while his brain was offline, he had incredibly vivid memories of being a 19th century surgeon in London.
Wow.
He saw the instruments, the clothes, the procedures.
Accurate details. Stuff he shouldn't have known.
Accurate details he hadn't studied. Sheldrake suggests this could be memory transfer. Usually you resonate with yourself, your past self. You are the most similar thing to you. That's why you have your memories.
But if my tuning is disrupted by a coma, for example.
If you are in a coma or have a major organ transplant, your frequency might shift. You might accidentally tune in to someone else who is very similar to you, like another heart surgeon from the past. You download their file because your passwords matched.
That explains reincarnation memories without needing a soul to travel. It's just cross signals in the cloud.
Exactly. It's a resonance model.
And this leads to the final concept, self-resonance.
This is the practical takeaway. We think we are a continuous person. But Sheldrake says you are continuous only because you are constantly resonating with your past self. Yeah. You are a wave that keeps reinforcing itself.
So my habits are literally the glue holding me together.
Yes. And that means if you want to change, you have to break the resonance. You have to stop tuning into the old you. And conversely, if you start a new habit, a good one, You aren't just helping yourself.
I'm helping the field. I'm making it easier for other people.
You are cutting a new groove. Every time you overcome an addiction or learn a language or practice kindness, you are making it slightly easier for everyone else in the species to do the same.
You're uploading a better signal to the collective cloud.
You are.
And every time I doom scroll,
you're digging that ditch deeper for everyone.
Well, on that terrifying but empowering note, I think we'll wrap up. We've gone from crystallizing sugar to telepathic rats to the cosmic responsibility of our own habits.
It's a lot to process, but it makes the universe feel a lot less lonely, doesn't it?
Yeah. It really does. Nothing is forgotten. Everything connects. Thanks for listening to The Deep Dive. I'm going to go do my French lesson now, for the good of the species.
Merci. See you next time.